So here we have a system consisting of a motor connected to a gearbox, which is in turn connected to a drum, as shown in this figure. So it's to be designed to lift a mass of 2 kilograms. The specifications of the 8-volt motor selected for the system are shown in this table. So for each of our calculations, we're going to assume that the system is operating at steady state, which is quite handy. So for part A, we're asked if the drum with a radius of 2 centimeters is selected, what torque is required at the drum to be able to lift the 2 kilogram mass, and we can assume that the drum is 100% efficient. Alright, so what I'm kind of picturing with this system is that we have a motor, give it a little M, and that's connected into a gearbox, put GB, and that this is then connected to a drum, and this drum has some string around it which is able to then lift the mass which is connected. So as you rotate this, it means that this could go up, or you rotate it the other way, it could go down. So for part A here, we're told that our drum is what we're focusing on, and this drum is going to have a radius of 2 centimeters. So that's this distance in here. And we need to figure out the torque that's required at the drum to lift the 2 kilogram mass. So this here is 2 kilograms, and that's going to control how much force, I guess, is inside the string, or the tension in the string. So if I mark in here in our diagram the force that's being applied, we can calculate it from the mass as being equal to the mass times gravity. So in our case, we're lifting 2 kilograms. So I can sub this in as 2, gravity is 9.8, so we end up with 19.6 newtons for the amount of force in the string. Convert this to a torque, okay, which is kind of like the rotational load that needs to be applied. So we can do that from our equation that relates torque, force, and radius. So we know that torque is equal to the force multiplied by the radius, or the distance at which it's applied around that rotational center. So our force we've just worked out to be 19.6, and our radius we've been given as 2 centimeters. So if you pop that into a calculator, it comes to 39.2, and it's going to be in Newton centimeters, since the force was in newtons and the radius was in centimeters. So the other thing, I guess, just to take note of is that we were told the drum is 100% efficient, which means we don't need to scale this up to account for any losses or inefficiencies in the system. So that there is my answer for how much torque is required at the drum in order to provide the lift required. So if we move on to part B, we're told that if the motor is to be operated at maximum efficiency, what gear ratio is then required? You should assume the gearbox is 85% efficient. Alright, so we're interested here in the gear ratio, and we have an equation for gear ratio which relates together the torque out of the gearbox and the torque into the gearbox. So that's T out and T in, and this N looking thing here is the efficiency of the gearbox, in our case 85% or 0.85 in a decimal form. So if we go and have a look at our diagram here, the torque out of the gearbox is essentially what goes into the drum, and we've just figured that out to be 39.2 Newton centimeters. So I'm going to mark that in our diagram here. So we also need the torque that goes into the gearbox, and that's equivalent to the torque that comes out of the motor. And we're given some information about that. We're told that we're operating at maximum efficiency. So if we look at our specification for the motor, we've got maximum efficiency here, and we've got a row that gives us the torque. So we know that if we operate at maximum efficiency, the torque from the motor is going to be 0.18, and the units we're told here are Newton centimeters. So I'm going to come down here and substitute it into my equation. So the torque out, is going to be the 39.2. Torque in is 0.18. Both of those are in the same unit, so they're going to cancel. And our efficiency, it's even marked in the diagram, it's 0.85. So this works to 256.2, and it doesn't have any units. We just said that those cancelled, and efficiency doesn't have units either. It's purely just, a ratio of number of teeth on one gear to number of teeth on the other gear. So moving on to part C, we're asked what rate the mass will be lifted at using this system. So the equation we're going to want to pick up here is that power is equal to force times velocity. And when we talk about this, since we're looking at lifting this mass on the end, right, we need to be considering the power we have available at this point in the system. So the force is quite easy, all right, that's going to be what we had before, this 19.6 newtons, and velocity is what we need to solve for. So if I rearrange this, it's going to be power divided by force. So we need to put a little bit of effort into figuring out how much power we have available at the drum. So at this point, essentially it feeds from the gearbox to the drum. So if we can figure out how much power we have coming out of the gearbox, that's going to be the same as the amount going into the drum, and in fact out of it, since we have an efficiency of 1. So if we come back to this step, we should be able to figure out power coming out of the gearbox. And we have an equation for power from a rotational form as being equal to the torque multiplied by the angular velocity. So if we scroll back up, we know the torque happening at this point, but we don't know what the angular velocity is of the shaft here that comes out of the gearbox and then connects straight into the drum. On this side, however, we should be able to draw that out because we know we're operating at maximum efficiency for the motor, and there's a a row here that gives us speed. So we can see at maximum efficiency, we're going to get a speed out of the motor of 100 radians per second. So let's mark that in. Now we know what our gear ratio is. Okay, we already solved for that in the previous step. It's 256.2. So actually what we can do is use this gear ratio to figure out what the angular velocity is going out of the gearbox. Once we've got that, we should be able to combine these two together to get the power available at the drum. All right, so let's start off with figuring out what the angular velocity is coming out of the gearbox. So we'll do that as a side step. I'll start it off with gear ratio. So the equation here is the gear ratio is going to be equal to the angular velocity into the gearbox divided by the angular velocity out of the gearbox. Now we want to find out, so I'll rearrange this, and we get that it's going to be equal to omega in divided by the gear ratio. So we can substitute in. We said that our going in is going to be this 100. And our gear ratio is this 256.2. So if you put that into a calculator, it comes out to 0.39 and the units are going to be radians per second. Alright, so let's draw this back now to our power calculation, because we said that power in a rotational form here is going to be equal to the torque multiplied by the angular velocity that we have. So if this is 0.39, we just solve for, we can multiply these two together. So torque, 39.2. Now this is in Newton centimeters. So if I want to convert that to base, I'm going to times it by 10 to the negative 2 to go from centimeters to meters. And then I need to multiply by the 0.39, which is already in base. So overall, if you pop that into a calculator, you end up finding that you have 0.153 watts available to you at the very end of this system. Okay, so it would have started much higher back here, but over time we drop and drop due to the inefficiencies or losses within the system. All right, so now that we know the power available to us, we can take it back over here and figure out what the velocity would be. So we've got 0.153 divided by the force, which we said way back here was the 19.6. And this one works out to be 0.0078 approximately, and it's going to be in base units because we were in watts and meters, watts and newtons for the force, and the base for velocity is meters per second. So this is quite a small number. If you wanted to make it, say, into centimeters per second, you could just multiply it by 100, and that would go to 0.78. So this here is my answer for how quickly we're able to raise that mass. So we've got one part left, which is figuring out if the mass needs to be lifted 30 centimeters, how long is it going to take? So we're going to use our answer to part C in this, and we know that velocity is equal to the displacement, which I'll call S, divided by the time. So in our case, we want to find the time taken, so I can rearrange this equation. And we just need to substitute in our information. So the distance or the displacement that we want to go is 30 centimeters, and the speed at which we're doing it is 0.78. So this comes to about 38.4 in seconds for the time it would take to lift it all the way up to where we wanted. So that's pretty much all there is in terms of this video.